Welcome to Physics and Reality with Prof. Stuckey. I'm Emeritus Professor of Physics, Dr. Mark Stuckey, and in this video I'm going to explain how some people account for the violation of Bell's inequality by opting for the violation of statistical independence using superdeterminism or retrocausality. When I'm done, you'll appreciate why this solution to Einstein's entanglement has very little support in the quantum foundations community. In order to keep this video relatively short, I'm going to omit a lot of details. If you want to see those missing details, you can read our 2024 book with Oxford University Press, Einstein's Entanglement. To introduce quantum entanglement and the violation of Bell's inequality, I'll use David Mermin's famous paper, Bringing Home the Atomic World, Quantum Mysteries for Anybody, that Richard Feynman called one of the most beautiful papers in physics that I know. I will then use the Mermin device to show what the violation of statistical independence means. Here is Mermin's device with a source that emits a pair of quantum entangled particles towards Alice and Bob's detectors in each trial of the experiment. Mermin assumes that Alice and Bob randomly and independently select measurement settings 1, 2, or 3 in each trial, and the measurement outcome is either red, R, or green, G. The experiment produces two facts. Fact 1 is that when Alice and Bob happen to choose the same detector setting, case A, they will always get the same color outcome. Half the time both are red and half the time both are green. Fact 2 is that Alice and Bob only get the same color outcome in 1/4 of the trials when they happen to choose different detector settings, case B. What's so mysterious about that? Let's start with fact 1 about case A. Mermin writes, why do the detectors always flash the same colors when the switches are in the same positions? Since the two detectors are unconnected, there is no way for one to know that the switch on the other is set in the same position as its own. The particle properties must be coordinated in some way so as to produce the same outcomes for the same setting numbers when the particles interact with the detectors in each trial. Mermin calls these hidden deterministic particle properties instruction sets and writes, it cannot be proved that there is no other way, but I challenge the reader to suggest any. Mermin assumes the particles cannot know how they will be measured until they arrive at their respective detectors. This is called statistical independence. Superdeterminism, with its conspiratorial control over measurement settings, and retrocausality, with its backward in time causal influences, violate statistical independence. Mermin also assumes Alice's particle cannot know how Bob's particle is measured before it renders an outcome at Alice's detector, and vice versa. This is called locality. Bohmian mechanics, with its faster-than-light pilot wave, violates locality. So let's see what happens when we assume instruction sets are responsible for the Mermin device outcomes. You can see that fact 1 about case A is satisfied. No surprise there, that's why we picked instruction sets. But you can also see that instruction sets do not reproduce fact 2 about case B. Fact 2 says only 1/4 of the case B trials will be the same color, but instruction sets give us the same colors in 1/2 of case B trials, when all 8 instruction sets are produced with equal frequency. If only instruction sets with 2 red and 1 green, or 2 green and 1 red are produced, then case B will produce agreement in 1/3 of all trials. The only other instruction sets are red, 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 and green, green, green. And these two instruction sets increase the total agreement in case B trials. Thus, the Bell inequality for the Mermin device is that we must get agreement in at least 1/3 of the case B trials. And quantum mechanics predicts only 1/4 agreement in case B trials. That is, it predicts the violation of Bell's inequality. As Bell states in the opening of his famous paper, the paradox of Einstein, Podolsky, and Rosen was advanced as an argument that quantum mechanics could not be a complete theory, but should be supplemented by additional variables. These additional variables were to restore to the theory causality and locality. That is, Bell explicitly assumed causality and locality in deriving his inequality. The additional variables were represented by instruction sets in Mermin's paper. Consequently, most people believe that any causal account of how quantum entanglement violates Bell's inequality must violate locality. However, there is another way to account for the violation of his inequality that Bell himself admitted later. In a 1985 BBC radio interview with Paul Davies, Bell said, there is a way to escape the inference of superluminal speeds and spooky action at a distance, but it involves absolute determinism in the universe, the complete absence of free will. Turns out free will is an aside. You don't really have to take that into account, but we'll ignore that. Suppose the world is superdeterministic, with not just inanimate nature running on behind-the-scenes clockwork, but with our behavior, including our belief that we are free to choose to do one experiment rather than another, absolutely predetermined, including the decision by the experimenter to carry out one set of measurements rather than another. The difficulty disappears. There is no need for a faster-than-light signal to tell particle A what measurement has been carried out on particle B, because the universe, including particle A, already knows what that measurement and its outcome will be. Bell was referring to the violation of statistical independence, which is the assumption that there is no correlation between measurement settings and hidden causal mechanisms. Here is how the violation of statistical independence can account for facts 1 and 2 for the Mermin device. When the instruction sets are red, red, green, or green, green, red, Alice and Bob choose measurement settings 1, 1, 2, 3, and 3, 2 twice as often as the other 6 possible measurement pairs. When the instruction sets are red, green, red, or green, red, green, they choose measurement settings 1, 2, 2, 1, and 2, 2 twice as often as the other 6 possible measurement setting pairs. Finally, when the instruction sets are red, green, green, or green, red, red, they choose measurement settings 1, 3, 3, 1, and 3, 3 twice as often as the other 6 possible measurement setting pairs. Remember, Alice and Bob have no idea what the hidden instruction sets are for each trial. So as far as they know, their source is faithfully reproducing the same Bell state in each trial of the experiment, and they are choosing all 9 possible setting pairs with equal frequency. The causal mechanism for retrocausality or superdeterminism must account for this behind-the-scenes conspiracy, no matter how measurement settings are chosen, monkeys throwing darts or the light from distant quasars. Here is how statistical independence is violated via retrocausality. Information about the future measurement settings is available at the source prior to the entangled particles being emitted. And here is how statistical independence is violated via superdeterminism. A causal mechanism in the past of the experiment is responsible for what the source emits and what measurement settings are chosen in each trial of the experiment. Anton Zeilinger complained about the violation of statistical independence, stating, "When I do physics, I believe I can ask free questions of nature to find out something new. If nature is controlling the questions I ask, nature could totally fool us. It would be the end of science." To see how far in the past a superdeterministic cause has to reside to explain the violation of Bell's inequality, Zeilinger's research group used light from quasars located billions of light years away in different directions in the sky to determine measurement settings. Since his experiment still violated Bell's inequality per quantum entanglement, he concluded that the superdeterministic causal control over his experiment had to reside almost all the way back to the beginning of the universe. Here is the result of a 2025 survey by editors at the journal Nature, in which 1,101 researchers in quantum foundations, myself included, said which interpretation of quantum mechanics they preferred. As you can see, superdeterministic and retrocausal theories, that is, those that violate statistical independence, have very little support. This was a very cursory introduction to superdeterminism and retrocausality. We provide more details, such as Hance, Hossenfelder, and Palmer's supermeasured approach to superdeterminism, and Wharton and Liu's path integral approach to retrocausality in our 2024 book with Oxford University Press, Einstein's Entanglement.